This diagram represents a parallel circuit junction. So you can see this is the point, the current in this particular case, the total current is 11 amps. It's coming into this junction. Now that current will divide according to the resistance or the magnitude of the resistance. Now current always likes to take the path of least resistance. So the smaller the resistor, the greater the amount of current that will pass through it. So if we apply Kirchhoff's current law in this particular case, we have I1 is equal to I2 plus I3, which works out to 11 amps. So the current going into the junction divides. Now the division depends on the magnitude of the resistor that the current is running towards. Now this is an example of the junction incorporated into a whole circuit, and you can see at this point here the conventional current comes in. We've got those 2 points, so the total current now I1 and I2, most of the current will take the path of least resistance. Now that is determined by the magnitude of the resistor. Let's now have a look at an example of Kirchhoff's voltage law and how it applies to this particular circuit. So our total current running through the circuit, this is a series circuit, so we get a potential rise of 18 volts across the battery, and if we use our gravitational potential energy analogy, you can see the potential rise in the circuit. So that represents our potential increase, what is provided by the circuit, and in this case it's 18 volts. Now here we have a potential drop. We've got a resistor that has a resistance of 0.5 ohms, and you can see the points between there and there. There is a very slight potential drop, and that potential drop is 1 volt. So that's how we would calculate it or determine it. Then as the current moves along between this point here and this point here, again you can see there is no potential drop because conductors do not represent significant resistance. So there is no potential drop, so we say the potential drop is 0 volts. Now the potential drop between this point at 17 volts and this point is 17 minus 5, which is 12 volts. And you can see there's quite a steep drop in the potential energy there. That's equivalent to 12 volts. The potential drop across resistor 2, which is this resistor here, 5 volts minus 0 volts. That gives us a potential drop across that resistor of 5 volts. So to find the total potential drop across each of the resistors, according to Kirchhoff's voltage law, it must be equal to the potential rise, or the total voltage. So what we have is the total voltage we know is 18 volts. Drop 1 is equivalent to 1 volt. Drop 2 is equivalent to 12 volts, and drop 3 is 5 volts. Adding those together, we get 18 volts. After this potential drop, there is a potential difference of 0 between those 2 points. The charge has to come back to the battery to gain potential energy or increase its potential again, so that this process continues as long as charge is available. Now that we've made the link between charge and current and the energy of the voltage, we can start thinking about how this translates to energy output. In other words, how can electrical energy be converted into other types of energy like light or heat using an electric circuit? So let's just analyze this practical example. So we have our electron or negative charge flow in this particular case, because we're talking about a negative Q, so it's running from low to high potential, the positive being high potential. Now the headlight in this particular case is designed to convert the electrical energy into light energy, obviously, for driving in the dark. So let's say if this was a car headlight. Now the energy supply, or the potential difference supplied to run this current and therefore to run the headlight, is 12 volts. And if we think about the electrical energy in joules, because we talk about energy, and with unit 1 when we looked at thermal energy, we said regardless of what type of energy it is, the fundamental, the standard international unit is the joule. So how do we now think about this energy in a particular given time? Well, one of the things that every electrical device, every resistor contains, is a rating. We call that the power rating, and really what it tells us is the amount of energy the electrical device uses for every second that it's on, that the current is driving it. So we can say that the power has a standard international unit we call the watt, and in order to think about watts, in other words the power rating of an electrical device and the energy, well, we say that 1 watt is equivalent to 1 joule per second. So what that means is the rate at which energy is used by the particular device. The resistance supplies enough resistance to produce a power rating of whatever watts, whether it's 40, 60, 100, and that would represent the joules per second. So power is measured in watts, and 1 watt is equal to 1 joule per second. Energy is measured in joules, and of course the time which the current runs in the circuit, in other words a time between on and off, is the time in seconds, which determines the amount of energy used and the power determined by the power rating of the resistor. So now we can think about power, or the power rating in watts, as energy divided by time, or alternatively we can think about energy as power times time. There's your watt, there's your joule, there's your second. Now we can also relate this power to the voltage of the circuit, because in previous lesson we said that 1 volt is equivalent to 1 joule per coulomb charge. So if we're calling the voltage a measure of energy of charge, then the unit for energy is the joule and the unit for the charge is the coulomb. So the power supply provides this, which is energy divided by Q, which is charge. And we also know that the current is represented by the amount of charge that flows per second, or coulombs per second, which in effect is equivalent to 1 amp. Also, from Ohm's law, we know that V is equal to I times R, where the current and the resistance in ohm is equivalent to 1 volt. And you can see the equivalence here if we say that 1 volt, which is 1 amp times 1 ohm, can also be equivalent to 1 joule per coulomb, according to this equation. So in conclusion, we can determine the power rating, or the amount of power that's dissipated, or the amount of power that's released by a resistor in an electrical circuit, using this equation P equals IV, and we can actually combine Ohm's law in this because we can substitute here for V, or we can substitute for I based on the appropriate resistance. So this slide summarizes our definition of electrical power in a circuit, and we say when there is a current, a voltage, and the power delivered to the circuit is related by this equation, P equals I times V, and also the unit for power is the watt. So 1 watt is equivalent to 1 joule per second, which is equivalent to an amp times a volt. Now, whenever we put an electrical device in a circuit, whether it's a light bulb or whether it's a television or whatever, it's the resistance that actually is involved in releasing the energy. And every electrical device has a power rating which tells you the amount of energy used per second. So this equation, P is equal to I times V. Now we also know that V can be equivalent to IR from Ohm's law. So that gives us the power is equal to I squared times R. Alternatively, instead of substituting for V, we can substitute for I, and I equals V on R, so we can put in V on R times V, which gives us power equals V squared on R. So these are the equations that we can use to quantify certain current, power and voltage measures and then convert them to energy in a circuit. Let's have a look at a problem-solving type question where we can use our understanding of voltage, current, power and energy to solve a real-life problem. So we've got here the current in a 3-volt battery, it's in a pocket calculator, is 0.17 milliamps. So this is the amount of current it draws in its normal operation. If it's being operated for 1 hour, the question is how much charge flows in the circuit during that time. So to solve this problem, we need to use the equation current equals charge per unit time, because that's how we defined current. We defined current as the amount of charge that flows through a particular point in a particular time. Now we want to find the amount of charge, so we just rearrange this equation. We know the current is 0.17 milliamps and the time is 1 hour. Now we must convert that to seconds. So that becomes 0.17 by 10 to the minus 3, so that's your milliamps. You simply multiply by 10 to the minus 3. And obviously 1 hour is equivalent to 3,600 seconds, or 60 seconds in a minute, so 60 times 60. And from that we can come up with a quantitative value. There is 0.61 coulombs of charge that flows in that 1 hour. So part B, how much energy does the battery deliver to this calculator circuit? So this time we know that if there's 0.61 coulombs of charge, we know that each one of those charges carries a small amount of energy, and in 1 hour, what does that all energy add up to? So let's have a look how we'd solve that. Since we know from a previous discussion in this video, 1 volt is equivalent to 1 joule per coulomb. Now that 1 joule is a measure of energy, and the coulomb is a measure of the number of electrons that flow. So from that we rearrange this equation. We can say the voltage is equal to the energy in joules divided by the charge in coulombs, or alternatively, to find the total energy, we've got energy equals Q, the total number of charge, times the voltage that drives the charge. From this we can put in our values. We know that the total charge from part A is 0.61 coulombs, and we know that the battery is 3 volts. Now alternatively, we can actually, instead of writing 3 volts here, we can write 3 joules per coulomb, because based on a discussion we had earlier, we defined volt as being joules per coulomb, and you can see this is convenient because then the coulombs cancel out. The question says how much energy does the battery deliver, so we're looking for an answer in joules. So on that basis, our answer is the battery delivers 1.8 joules of energy to the calculator circuit.